Okay, guys. So let's get to it. Uh, Feeling tired? I hope you. I hope I can be sharp for both exposition and taking questions. If I seem slow or down on energy, just help. Okay, so the plan for today is continuing the presentation of this basic framework of statistical decision theory. I think we've covered a bunch of things that I really wanted to share with you. I think there's this very simple definition of what's statistical model, very simple and nice definition of what's a statistical decision problem. We said that the focus is figuring out or trying to use this framework to pick good decision rules. And last class we started thinking about one of the general principles that we have for picking or recommending decision rules, right? We did this base principle, which is performance of these different decision rules is typically going to be different in different parts of the parameter space. So if you tell me how you want to weight that performance, I can figure out what is the rule that has the best average performance. And I think that's a good way of thinking about how you can use this idea of bringing in a prior to the table, updating it, and creating a rule based on it. And then we have this discussion about admissibility, right? This notion that you definitely don't want to use any decision rule that is dominated. So decision rules that are not dominated are called admissible. That's not defined in reference to any weight. It's a global definition. And we had this result that I presented that under some conditions, if you have a decision rule that is based for some weight function prior, then that rule is going to be admissible, right? I kind of like gave you this picture and argued that under some conditions you're going to have actually the reverse implication. Any rule that makes sense in the sense of being admissible, there's going to be a prior under which you can recover. This kind of results, I think the name of in the literature of this type of result is a complete class theorem. So if you get curious about these things, you can Google it. Might have some reference in the notes. So what I'm going to try to do today is something a little bit more challenging, which is talking about the minimax principle. And so the way we define this is like, I'm going to keep on this object that I introduced as class, the risk function.
Can I ask just about this complete class theorem?
Yeah.
It feels like a very powerful result to be able to kind of say, like, we sort of accidentally stumbled into this sort of Bayesian framework, but then actually, any sort of good rule that we come up with, it corresponds to some prior, which feels like, maybe we don't have so much objection to putting down prior if that's kind of what the good rules are exactly.
Yeah.
And that just feels like a very powerful result that sort of just fell right out of the definitions.
That's how I feel. I think it's really just a really amazing result, but I don't think.
Baked in, that's the thing that I'm kind of confused about. We didn't set up a Bayesian framework, but then we kind of got one. I don't know,
I mean, I think it's just magical, right? But I mean, if you think about it, there are instances that are not very different to it. It's like, so I'm going to tell you a result that it's also among my favorite results in econ. First welfare theorem, right? You bring this notion of efficiency that has nothing to do with prices, and then you kind of like create this price mechanism to decide who gets what. And then this miraculous connection arises, right? That anything that is an equilibrium under some assumptions leads to this efficient allocation. And then you have something that looks like the reverse, right? It's the second welfare theorem. Maybe as cool as the first one. I like more the first one than the second, but it's the same idea, right? Like there is for any efficient allocation, there is a price vector and some initial allocations of goods to consumers such that these things happen. So I really think these results are pretty cool. Yeah, I like this notion a lot, but not everyone. Yeah, I don't want to come across as I'm preaching because that's not what I just when I first time I saw these results, I thought it was kind of exciting, and yeah, I think it's just a good thing to keep in mind. Yeah,
Thank you.
yeah, awesome. Thanks for the question.
So, related to that, does this, I can imagine that this relies heavily on dogmatic priors, right? If things are admissible, there's some point in the parameter space where it is undominated, and so you construct a prior that's dogmatic at that point, and of course it's going to be.
Not necessarily, right? Because the dominance again, it's like it's these global criteria, right? So actually, some of these results you can. I mean, they don't tell you exactly that the priors are going to be full support, but some of these things you have finally many points over which they are supported, but you know it's not that obvious. The construction is not that obvious. Yeah, it's not just dogmatic priors. Yeah. Also, well, so for the minimax principle, then we said that we are doing some working with a loss function. Just to remind you where I'm at, so I'm taking this expectation with respect to the distribution of the data that is prescribed by parameter theta. And so we said that the problem that we are going to be interested in solving is one in which you look at the worst case performance of a particular decision rule, worst case performance over the parameter space, and then you try to optimize this worst case performance. Right? And so any decision rule that solves this problem is what it's called the minimax rule. And sometimes this number, which is just a value function that optimized value function that defines the minimax problem, it's called the minimax value of a decision problem or whatever. Very similar to what you see in zero-sum games, two-person zero-sum games. Right. So the way in which I'm going to try to present the approach for solving these problems, it's kind of like the approach that I have used in my own work. It's like a little bit of a brute force thing. I'm sure that there are probably a couple of smarter ways of doing it, but the principle is really trying to figure out what are reasonable bounds for this objective function, and then trying to figure out a way in which the bounds for this objective function meet. So I'm going to try to make that a little bit more transparent. So what I'm going to try to do is just give you a sense of what these bounds that I have in mind are coming from, lower bound and upper bound. And then I'm going to try to go to a specific example, and I'm going to try to just work out the example so that you see how the construction works. I'm going to use today I'm going to use the policy problem. And I mean, depending on where we go, if I have more time, I might use this prediction problem that I also want to talk about. But yeah, let's see what we. So I'm going to say that there's like an upper, lower bounds for minimax problems. So let me start with the one that I think it's kind of like the one that allows me to make a direct connection to the Bayesian decision rules that we just discussed. And kind of like, you know, even if you are a person that, as we were talking with Jake, I think that there's some sort of magic in this theorem that I presented, but you know, to implement a particular decision rule, you still need to bring a prior to the table, and that, you know, that comes with certain problems because you need to pick a prior. But even if you don't like the idea of using one of these decision rules, Bayes decision rules are going to allow me to get a sense of how bad this number can be, okay, or how good this number can be. Okay, so for the lower bound, what I'm going to use is something very simple. You're actually going to laugh at me for the simplicity, but there's a very simple connection between worst case performance and average performance, right? So could you tell me just quickly what type of relation you can think about, like average performance and worst case performance? Yeah.
The worst case has to be like weekly less than average.
Perfect. So there's just this common sense thing that's why I like presenting this, that we can very quickly establish a relation between, you know, what happens if I look at the average and what happens if I look at the worst case. So let me start just by noting that I'm going to write first what worst case means here. Right? That's what I mean for the worst case performance of a particular decision rule. And so, remember, this thing over here is the risk, right? So worst case performance means that I have I'm incurring into a very large risk. So what I want to claim is that for any, so now we're going to use the word prior, pi, the worst case risk over the parameter space is going to be at least as large as the average value of the risk under the prior pi, right? So that, no disagreement. Perfect. Okay, so now, so this is still not quite the bound that I want to have, because it's a bound that depends on the decision rule, and you know, this thing obviously has been optimized, so I need to somehow remove that dependence on the decision rule to get a more useful sense of how I can bound that minimax value from below. So good news is that based on what we discussed last class, we can do that, because you know, this is the average performance on the prior pi of a particular decision rule D. And this is guaranteed to be larger than or equal than if I actually try to figure out what's the best performing rule in terms of these average criterion, right? Does that make sense? So now just, so I'm going to keep this one in here, but if you further allow me, I'm going to put it in parentheses just in case I need to use this later, but just to make it a little bit more visual, in the case where you actually can achieve this in Feynman, and you know, you denote d pi as the base rules that we discussed last class, then this is the same as the average value of the risk that you get by using, I think this is the notation that I used last class, right? The base decision rule according to prior pi. Yep.
So I think one thing I'm confused about
Yeah.
is going from the first inequality where
This one?
on both sides of the inequality
Yeah,
you
yeah.
have the same decision rule,
Same decision rule.
and then when you go to the second line,
Yes.
you are allowing me to choose the one with the lowest average risk.
Yes. Yes, exactly. And that's just that the infimum by definition has to be smaller than or equal than this guy, right?
Right, okay.
Yeah. So that's the only thing that I'm doing. Again, like I try to only present things that I really just can digest with a couple of lines, because if not, that increases the chances that I make mistakes. So this one should be like this. Okay, so then this is one possible way of generating these lower bounds. of course, this is valid, and that's kind of like the surprising part for any pi. So for any pi, I'm going to be able to kind of like sharpen these bounds, right? Okay, so I'm going to leave this one over here for a second, and I'm going to give you an idea of how to derive an upper bound. And then once that I have that, I'm going to come back to this lower bound derivation to kind of like just try to convince you that this is one way of deriving these lower bounds, but it's not the only one, okay? So there are other things that, and they have names in the literature. So this is just a very typical one that connects with the base decision rules, and it's useful for the problem that, that I'm going to use as an example. Yeah?
Sorry, going from the first line to the second line of the position,
Yes, first line to second line.
we're extending the lower bound to be smaller, right?
Yeah.
I thought we're going the other direction of raising the lower bound.
Not quite. Right now, I just want to have a lower bound that doesn't really depend on what decision rule I put there, right? Because so if this is what I want to, bound, right? I think if I now take infimum on this side no longer depends on D, right? So I can just give you a bound based on something that no longer implies this optimization over the space of decision rules, right? You see that? I mean, it's just like add the infimum over here because this bound is free from decision rules. This becomes the universal bound on this thing, right? So let me just write it right. So I'm going to say that A. So if I call this equation 1, so A implies that 1 is larger than or equal than, and let me use the term in parentheses, for any pi. That makes sense? Okay. Perfect.
You don't want to depend on D, but it depends on theta?
No, because the theta has been integrated out by pi, right?
Okay.
So this bound kind of like only depends on pi. Yeah.
We were talking about this after yesterday's class, and I'm wondering if, let's call theta star the one that solves the soup over RD theta.
Yep. Need not be unique.
Okay, need not be unique.
Yeah. And need not be finitely many. It could be, in the example that I'm going to show you, and it can depend also on the decision rule, right? So that theta star can be moving around depending on what decision rule you put in.
Right. I think, okay.
Yeah, so that's important. That's important. Okay, perfect. So, so then let me tell you a little bit about how I'm thinking about here is a way of getting a very trivial upper bound on the minimax problem. Okay. So I'm going to introduce notation. I'm going to call. Say, should be kind of like a calligraphic D. A strict subset it's a strict subset of decision rules. Okay, so meaning that I take a set of all possible decision rules, and here I'm imposing some restriction on them. Now the restrictions, they can vary in what they are, but if you think about the most extreme restriction comes from saying that I just want to consider one particular rule. For the cases of testing, I think we had this discussion about like, well, what if I'm a person that only wants to look at decision rules for which the rate of type 1 error is below alpha? That could be one such a class. Okay, perfect. So one thing that it's going to happen is that once that you restrict yourself to a particular set of decision rules, then again, an obvious inequality is that if you try to take the infimum of any objective function, right, there's really nothing that it's essential to the risk. But if you try to take the infimum out of any function, if now you, instead of allowing yourself to search over all possible decision rules, you constrain yourself to look only inside the class D. The class D could be could have a singleton. There's going to be a very natural relation between the values of these two problems, right? Again, this is maybe not as obvious as the relation between the worst case and the average performance, but it's in the same league, right? So anyone just wants to tell me quickly which one is going to be larger or smaller, and just give me a quick argument, just a heuristic argument of why? Perfect, right? So this one is going to be smaller just because I'm trying to minimize this function over a very large set, and I put an artificial constraint, so that can only make this infimum to be larger, right? Okay, so then one thing that I have right away here is that I've sandwiched the minimax value, right? So I'm just going to write that explicitly. It's a note that A and B imply that one is going to be lower bounded by this is for any pi, and upper bounded by this is for any t. Right? Okay. So if you're here, if you're with me up the way to here, so I'm just going to give you a quick little puzzle, and so I'm going to write a quick claim in the board, and then you tell me if you think that claim is true or not based on what it's written in the board. So claim. Suppose D star, so that's a base rule for an arbitrary prior pi, has constant risk in the sense of if I look at the risk of the star pi at any point theta in the parameter space, this is going to equal C for every theta in theta. So the claim that I just would like to get a sense of whether you think this is right or not, and if it's right or not, why. Minimax optimal means that the decision rule solves this problem over here. So I'm just going to write it here. It's just a quick brain teaser, just to see if you can manipulate these bounds over here. But so anyone wants to just give it a try? Yeah.
I'd say yes, because necessarily if like it's constant for all theta, and that means the supremum will be the same value, and then d pi star is already defined to be like the lowest, like the lowest value of expected value before the decision rule. So that should be the lowest value you could get.
Okay, so let me try to put it together, and then I'll ask you a couple of questions on the way. But I think you're totally on the right path. So I'm gonna start with this bound, right? So I said that d star pi has constant risk, and so that means that the lower bound for 1 is just that constant c, right? So the lower bound, I have almost for free that 1 is lower bounded by c. So now, how about the upper bound?
Then wouldn't it have to be like weakly greater than c, because this is like d pi
That's
star.
weakly greater, I think it's already here, right? I want you to think about this.
I mean, the upper, like, all right, it would be less than the upper bound, right? Because, again, we're selecting, like, a different decision rule, but, like, we already know that this decision rule has this, like, lowest constant c, so any other decision rule would only give us some value greater than c.
That's good. So let me try to rephrase it, and then you tell me if you agree. So this upper bound that we derived was for any subset of decision rules. I'm going to take the trivial set that only has this guy, right? So then this bound still applies. So now I'm looking at the worst case risk of that particular rule, and as you said, it's constant, right? So it has to be c. So I have c is now giving me an upper bound and a lower bound. So that means that 1 has to equal c, right? And by definition of what it means for a rule to be minimax optimal, then it has to be the case that this guy is minimax optimal because it solves that problem. Right? So I mean, that was one thing. Perfect. Okay. So that makes sense? So let me try then. I think what I'm going to try to do now is try to set up a simple example where I just want to see if we can try to solve together for a couple of rules that are base for this problem, and then using some of this construction of base rules to see if we can find the minimax optimal rule. Okay? So the example that I'm going to be using, let me put this thing over here. So the example that I'm going to be using is the example of the policy choice problem that we just described last class, or the first one, I can't remember exactly. But so I'm going to be thinking about a case in which we have a policymaker that is interested in deciding whether a new policy should be implemented or the status quo should be preserved. And the information that the policymaker has available is just some estimated effect of this policy, which I'm going to assume that it's normally distributed, centered around the true effect with some variance that I'm going to take as no. Right, so the action space that I'm going to be thinking for this policymaker is that A is binary. So you either do action 1 or action 0. 1 means that you implement the policy, 0 means that you preserve the status quo. And I don't think I'm going to use it at all in all of these constructions, but sometimes it helps if you just allow this policy maker also to flip a coin in case he needs to do it. Okay, so this is the statistical model, this is the action space, and the payoff function that we are going to be working with is the payoff function that I described during lecture, which says that if you decide to take action 1, which means that you implement this policy at scale, you get as reward the true unknown policy effect, or effect of implementing the policy. And I'm normalizing the payoff of the statu quo to be 0. Okay, so this is what we had in the notes. Okay, so I'm going to start, I'm going to do 2 things. So I'm going to try to just work out the base rule for this problem that you're going to see that it's going to be very simple. I'm going to try to do a version of the minimax because I'm not working with loss directly. This is a payoff function. I'm going to do maximin. So I'm going to look at the worst value of expected utility over the parameter space, and then I'm going to try to optimize for that. And once that I have that, I'm going to switch a little bit back to the regret loss induced by you, right? Do you guys remember this notion of regret? We talked about last class. It's you give yourself a benchmark. So you think about what is the largest payoff that you could get if you knew the true state of the world, and you use that to as a benchmark for the payoff that you would get for an arbitrary action, right? Now, just to have this thing over here, because I'm going to use it later, I'm going to try to give a more concrete expression for this one. And this is also, I think it's a good step when you're thinking about the setting of these problems and you're actually trying to take seriously the payoff function, just to figure out what would be the solution to this problem, because that speaks about what a person or what a policymaker that actually knows the state or the parameter that generated the data would do, right? So any leads or ideas on what is the optimal action and what's the optimized value of the utility function for this problem? So we are thinking about the case of a policymaker that knows what theta is. Yeah.
So if theta is greater than 0, then I would want to implement the policy, or else I wouldn't.
Perfect. So kind of like if you think about what's the optimal action, this optimal action so if I call A star theta, which is the oracle action, this is the oracle action, is going to be, you can write this as the indicator function of theta larger than or equal to 0. Right, and so that means that the optimized payoff is going to take a very simple form, right? Because, so I'm going to get the true effect of the policy, but only when this is larger than or equal to 0, right? Does that make sense? One way of representing this utility function is just the thing that I wrote over here. I can write it just as the product of the action and the parameter, right? It gives me theta when I set the action equal to A. It gives me 0 otherwise. So that means that the regret is going to be simply given by the state multiplied by the difference between the oracle action and the action that you take. Yeah, and so just a couple of things. The reason why we're going to be able to solve this problem, or one of the things, is that there are a bunch of things that I'm going to exploit over here. I have the Gaussian model. That's going to help me a lot. But also, and I think more importantly, the payoff function that I'm working with is somehow very easy to deal because it's linear, right? Like the state enters the payoff linearly. And that has implications, right? Because if you think about what I'm doing, if this is truly kind of like an average treatment effect of a policy, that means that this policymaker is, in a sense, risk neutral, right? Only cares about the mean effect. Okay, so that's the environment. Okay, perfect. So let me start doing a couple of things. Okay, so I want to first set up the problem of figuring out what's a base rule for this problem, right? And remember that a base rule, if I work with utility, you can simply set up the problem as what is the rule that maximizes expected utility. I could also do the same thing for the regret loss, right? I could say, well, you said that that's the loss, and you can now think about what is the rule that minimizes expected regret loss. So one thing that it's just a good exercise to do is that if I try to figure out the base rule that maximizes expected utility or the rule that minimizes regret loss corresponding to that utility, the solutions are going to be the same. Okay, and no worries if you don't see it at this point. I'm going to go directly and try to maximize expected utility, but this relation is going to hold. So perfect. Questions so far? Everything good? Perfect. So I'm just going to try to figure out what's the rule that maximizes expected utility. I have to pick a prior, so I'm going to pick a prior. I'm free to pick whatever I want. So I'm going to pick a prior that is so the first thing that I'm going to do is that the part that is hard for this policymaker is that he doesn't really know what's the sign of the policy effect, right? So if you knew what it was, if you knew what this sign is, the policy rule would be very clear. So one thing that I'm going to start doing is I'm going to try to put up a prior that kind of like respects some of the complications of this problem. Like this policymaker doesn't really know if I'm on the left or on the right of 0. So I'm going to give him a prior that puts mass on both of these subsets of the real line. But I'm going to do it in the way that I think it's easier, right? Like there are a bunch of distributions that put mass on both the negative part and the positive part of the real line. But I'm going to start with a discrete distribution that places mass on 2 points. So I'm going to call these minus theta star and theta star. And theta star is just some positive number. Does that make sense? I mean, I'm free to pick any prior. One thing relative to what we discussed yesterday is like, well, Pepe, the theorem that you proved said that in order for the admissibility result to kick in, you kind of like need to put a full support prior. and I could do something like that. I could pick up, say, normal prior and play with the conjugacy of the normal statistical model, and things would be the same. There's a result that says that if base rules for prior that is not necessarily fully supported or has full support, if it's unique, then it's admissible. So I'm not breaking the admissibility. I'm not going to show that, but just going to stick to this because it's a little bit simpler, okay? And so then, if I have a weight on these two points in the parameter space, I just need to specify what the probability is. And I'm going to say that I'm going to call pi star be the probability of theta star. Does that make sense? So that means that this guy just, it's not a PDF, but it's a probability mass function. You can think that this is being defined as pi of theta star. Does that make sense? Okay. And I'm just going to make this number to be strictly in 0. Okay, so now I'm going to try to solve this problem, right? Anyone can help me a little bit with just last class I told you that solving these average performance problems is difficult because we're solving an ex-ante problem, but we can always try to simplify our lives, or we can always simplify our lives by looking at this ex-post problem. Any idea of what, how I set up this ex-post problem here? What would I be needing to solve or compare? It's a binary action problem, so it's relatively easy to express it. So anyone can help me with this?
If you remember me correctly, but I think we said we'll take a draw the data and solve conditional on that, so I think that's the theta hat. So
Perfect.
solve the conditional theta hat.
Perfect. So what I'm going to try to do then is, what I'm picking now is actions for a particular draw of the data, right? So what I'm going to do is, I want to compare whether I should be taking action 1 or action 0. So I don't know what theta is, but I'm going to be thinking about a case in which I can compute the expected value of this payoff conditioning on the data, right? And I want to essentially do the comparison between this guy and this guy. Does that make sense? Okay, and so the subindex pi here means that theta, which is the thing that is being integrated over, has distribution according to the post theory. Okay, and that's because of the theorem that we worked out. We don't have to work that out again. Okay, so let me just simplify this expression. Anyone could just give me a sense of what this equals to? Just based on what we have in the board. It's going to be 0, right? So, okay, so evaluating one of them, it's pretty straightforward. Now, how about this subject? If I just want to simplify it, what would I need to write? Perfect. So the part inside is theta. So I just have to live with the fact that this is right. So essentially, the base rule is going to be given by the decision rule that picks action 1 if this posterior is larger than 0 and 0 in other case. Does that make sense? Okay, well, now pi is a distribution with a discrete support, right? So what I'm going to try to do is just see if I can do a little bit more of work to get a better expression of what this posterior mean is supposed to be. Okay? And so note that if I look at the posterior distribution, right? It's kind of easy to compute because theta has 2 values under the prior. So under the posterior, it has at most 2 values, right? So this is just going to be theta star times the posterior probability of theta star given theta hat, right? Plus minus theta star, because that's the other value that theta can take, times the other probability. But the other probability, I can just write it as, maybe let me save it as, I'll write it as that later. Does that seem reasonable? Okay, so let me just continue these things so that you see how I work this out. So I'm going to take that expression and so there's a common term over there that factors this difference. Yeah. Saying over here, it's minus theta, right? So it's the same thing. Yeah, sorry. So it's the 2 values that are in the support theta star and minus theta star. And we started with the assumption that this was strictly positive, right? So the decision rule can be written as you implement the policy if, remember, there are 2 values under the prior, theta star and minus theta star. So theta star is the positive one, minus theta star is the negative one. So you implement the policy if Does that make sense? Okay, and then it looks a little bit better than what I had before, but it's still like, well, what's the posterior, right? And so I can write this thing by looking at the ratio and comparing the ratio relative to 1, same thing. And this one, I have a better chance to compute it just because the way we define the posterior is the likelihood times the prior, right? So note that the ratio of posterior probabilities can be written as, so essentially, so if I let f denote the normal PDF, so this is going to be, the data is fixed, is theta hat. The mean is theta star. And then the variance of this normal is just some number sigma squared that we are treating as known, right? Then you have the prior. And what I want to know is whether this is larger than 1 or not. Right, so this is the likelihood ratio of normals, univariate normals that have the same variance. And I'm looking at two different parameter values. One is positive, one is negative. I'm not going to write the full exponential, but this one is easy enough to derive that I think I can skip it. But one thing that can be shown in this case is that the event or the set of values of theta hat for which this happened can be shown to be equivalent to the event in which theta hat is larger than the following threshold. Where these are the ratio of prior probabilities. Does that make sense? Okay, awesome. So I think what this is just saying is like, again, I looked at a very restrictive type of priors, because essentially with these priors they have to be supported in these 2 points. So I have flexibility still on where I put theta star and where I put the prior probability on theta star. But I mean, maybe just worth noting that theta star is restricted to be positive. So the type of decision rules that I'm going to be spanning as I move the prior is going to be threshold rules. So this policymaker is going to be willing to implement the policy if somehow the estimated treatment effect is larger than a threshold. So how much or how close to 0 this threshold is going to be will depends on the prior, right? So fix theta star to be whatever, we know it's a positive number, and make the prior probability of the effect of the policy being positive. So this ratio is going to be less than 1. The logarithm is going to make this number negative. So that means that the policymaker is going to be willing to implement the policy even if the estimated treatment effect is a tiny bit negative. This is kind of like not crazy, it's just a policymaker that is kind of like biased towards implementing the policy. So it takes a little bit less to convince him that it makes sense to implement the policy. Do the same exercise for the case in which the probability of the policy effect being positive is smaller. So this policymaker is biased towards not implementing the policy. It's going to make sense for him to put a larger threshold to implement the policy. And so these things are going to be optimal. As I move, as I said, the different values of pi star and the different values of theta star, I essentially get all possible threshold rules. So that's good news because all of those threshold rules are actually going to be base for some prior, and because of this result that I was mentioning, that the solution, the base rule that solves this problem is unique, and there's this theorem that says that if base rule is unique for a particular prior, then that base rule is admissible. So all those threshold rules are going to be admissible. Yeah.
So we were just looking at some statics with PyStar. I'm wondering if you have any intuition for why it's the case that theta star would show up in the denominator and sigma star would show up in the numerator. Do you have any intuition that can help us explain?
I mean, let's try to see if we can figure it out, right? I think that with theta star, I think you can there's a story for it, right? So if prior places tells you that theta star is very large, right? So that means that let me interact it with pi star, because I think that's going to make more sense, right? Because I think this only matters when I have difference in the prior probabilities, right? Otherwise, this threshold becomes 0. So, so theta star is defined to be positive. Now, assume that this one is smaller, right? So that this is the pessimistic or the policymaker that is biased towards the statu quo, preserving the statu quo, right? So that means that this policymaker is going to be having a smaller threshold, a positive threshold for implementation, because you're biased towards the statu quo. Now, if you make theta star very, very large, what this is saying is that that threshold for implementation is going to be getting close to 0, right? I think maybe the way of thinking about this is like, if you're biased towards the statu quo, which gives you a payoff of 0, kind of like the arguments that you have against not implementing the policy are probably not that strong if you're under your prior. There's the possibility that that policy has very large positive effects. Yeah.
In practice, how do we obtain theta star?
Yeah, that's what I'm saying. This is the same as picking a threshold, right? There is no, right now I'm not making any claim, just because an analogous question would be, in practice, how do I pick the prior? And there's really no question for that.
I have like two questions. The first question is that here we are working with point identification, right? We need
Absolutely.
system estimator theta hat for theta. So how does this example generalize to partial identification? Secondly, is like suppose like we are doing something like empirical based, like we estimate the prior pi, and then we form the decision rule by replacing a pi hat with the pi star. So that's like one reasonable approach. So
Yeah,
I'm
yeah,
wondering if
yeah.
there's another approach, like we incorporate this kind of estimation error of pi hat into a different loss function, and use a different loss function to
Yeah.
learn, like, or is there anything we can write with that?
Let me take the first two questions, because I think it might be easier to give you a sense of the first question, and also maybe you're kind of like in this problem, assumption that we're working with is that the estimated treatment effect that you that you have available for you, theta hat, is directly informative about the effect that you're interested in. That's theta, right? There are deviations of this problem, and it's also toy problems that have been worked out in different places. I have a paper where I have a slightly more general version of what I'm about to describe. But you can think about the case in which, so imagine that there's a distinction between the population where you can run the experiment and the population where you actually are interested in implementing the policy. Right, so that means that the estimated treatment effect theta hat reveals something about the effect on the policy on the population where you can experiment, but that need not be immediately informative about the population where you want to run the experiment, right? I'm a policymaker, I'm originally from Mexico, I'm interested in making a recommendation about making a policy change in Mexico, but I only have an experiment that was run, say, in the United States or somewhere else in Latin America. So that means that the pay of relevant parameter is not really identified, in the sense that even if I were able to run a very, very large experiment, I would not fully learn what the effect of the policy in Mexico is. Now, there are ways of bringing this notion of partial identification by saying, well, you know, what if you say that you know, the effect, the true effect of the policy in Mexico is at most k times the effect, or it's within plus and minus k, the effect of the policy in, say, Brazil. Okay. So, okay, so now if you run a very large experiment in Brazil, like with infinitely many people, you would be able to say something about the effect in Mexico, right? Hence the partial identification. So there are a couple of results about that problem, and I have articulated some of those in a paper that is on my website on decision theory for treatment choice problems with partial identification. So the first result is that you can do Bayes in the same way, because nothing changes. I mean, with the Bayes rules, there's a prior, there's a posterior, and you just figure out what's the payoff function. So that doesn't change. Now there are a couple of things that get problematic, because as we're saying, like the use of Bayes rules is kind of like cute, because somehow, you know, these rules, you cannot improve upon them. They make sense. We have a result in our paper that says that in these treatment choice problems with partial identification, anything that you can think about, any rule, and the way we say this in the paper is that regardless of how exotic or crazy this rule is going to be admissible. And there's a reason why, like when you cannot really fully pin down what would be the right thing to do if you were to fully observe the parameter in Brazil, there's always room for making any rule look good, depending on, you know, what you assume about where the true pay of relevant parameter is. So that's one thing. Then in the paper we also discuss what happens with this minimax regret stuff, and I think that one you'll see. I'm gonna solve for the minimax regret, or so I'm gonna present you the minimax regret solution for this problem, and this problem is going to be unique, and it's going to be a threshold rule, and there's going to be a threshold that gets pinned down. The case of partial identification, there are typically infinitely many minimax regret rules, so that's bad news. So yeah, so you can tackle this with partial identification, but the problem gets tricky. You know, you have to live with these features, and we have a couple of recommendations of what things you can do, so you can look at the paper. For the empirical basis strategy, though, one thing that I'll be very clear about this is that the empirical basis strategy, which assumes that you can quote-unquote estimate the prior, requires you to have additional information that you don't have in here. So you can't really estimate the prior if you only have one estimator for the treatment effect that you're interested. So you can do these type of things in scenarios where, say, you've run experiments in a bunch of different countries, and what you can assume about them is that they're all draws, they're heterogeneous, but they're all draws from the same distribution. So in that case, if you have a large enough cross-section of countries where you have experimented on, you can use those to estimate the prior, and implementing the Bayes rule with that prior has some large sample optimality-like properties. But you can't fully do that in the setup that I described, just because I only have one theta hat. So this idea of estimating the prior for these problems, I've also articulated this in two papers. One of them is in JET, the Journal of Economic Theory. It's called A/B testing with Gaussian priors, and I have another one in the papers and proceedings. And a similar idea is part of a paper at JPE that I co-authored with a bunch of friends, A/B testing with fat tails. So, I mean, if you're curious about just the empirical-based approach for these problems, but one thing is that all the empirical-based approach analyses that we've done for these problems have been done in the context of point identification. Yeah, makes sense? Yeah.
And then, can we find the prior so that the rule will not be like the threshold rule? Because it seems like within the prior, the posterior mean will be increasing in theta head, and so it will just cross the zero. So, I mean, is this result general for any prior only for the discrete functions?
So that's an excellent question. So I'm going to tackle you a bit. I have finally many times, so I cannot present all these problems for all these results for this problem. But you know, I kind of like told you that all these are base, and that means that all these threshold rules are admissible. But totally valid question. What you're asking is like, what if there are other things out there that make sense? So kind of like a cute result in the literature says the following. Consider only the class of decision rules that arise from threshold rules. So these are rules that implement if theta hat is above a threshold, okay? So focus on that class, call it threshold rules. Now, give me any other decision rule that you can think about, any other that you can think about that is not of the threshold form. So what could be it? Like maybe you flip your decision. Like if it's very large enough, you implement, but in between you don't know, and then you know you flip your signs, or you randomize, or you do whatever. So that would be an example of a non-threshold. So there's a result that says that the class of threshold rules has a property that makes it a complete class. What this means is that any other rule that you can generate, there's going to exist a threshold rule that improves weakly on the risk everywhere in the parameter space. So it's not dominance, but you are at least as good everywhere. So for these problems, there's no need to worry about that. So these things discarded. And coming back to these problems with partial identification, you don't have these complete class theorems because everything is admissible. So in these problems, you can give examples of things that are flipping a coin, for example, here is dominating. But it's not if you have partial identification. Yeah, okay, so let me just, so I did this exercise, so let me now do the minimax. Yeah. Yeah, sure.
Is there any aspect of inference in this problem? Like, I can just look at the
Yeah, no.
and then
No.
Take it as an estimator.
Yeah, no, that's a very good point. It's not part of the payoff function. Your happiness or unhappiness doesn't depend on whether your confidence interval covers the true parameter. It just depends on whether the policy choice that you make gives you good payoff. And because of that, there's really no reason for doing any inference in this.
So it sort of collapses to a point estimation sort of decision.
Not quite, because I'm also not estimating this thing. It's just like, in this case, it happened to be that the decision rule depends on the estimated treatment effect. But in these problems with partial identification, it's not that you're trying to estimate the identified set or anything. It's just the decision rules can be defined separately from it. Yep.
But making posterior theta hat is like just population, right?
It is. I mean, you can think that depending what you think about, but here the thing that pins down the thing is, say, the posterior probability of the two values, right? It's not even that I have to rely on the estimator. This one kind of relies on the estimator, but it need not. Okay, so then let me let me do one more thing then, and see if I can finish that. Let me see how I'm doing time-wise. Okay, so I think I can do two things. I'm gonna try to use these bounds that I showed you to figure out what's the minimax solution to this problem. And so the one thing that I just want to emphasize is that what I'm going to try to solve is the minimax regret problem. Just I'm going to be thinking about risk defined in terms of these regret laws. I need to delete a little bit more. Okay, so I'm going to give you a claim to make it less mysterious, but the way I'm going to prove this claim is by using these bounds. So the claim is that so I'm going to remove the pi because this no longer depends on pi. Okay, so that's a claim. So let's see how I'm going to go around and proving something like that. The easiest way for me to go around this is, I mean, I already have a candidate for this rule, right? So I'm going to use that to give a bound. So I'm just going to try to compute for this specific decision rule what's the worst case, right? So proof. Start by looking at right. So that's the first thing that I'm gonna start looking at. Is I'm given a rule and I'm trying to figure out what's its worst case. So that's kind of like taking this as a singleton. I don't need to take infimum anymore. And so here I'm just going to use the definition slightly, right? So regret here is kind of like if I just take the definition of regret and put the expectation, I'm going to get something like so without uncertainty, regret was just the difference between the oracle action and the action that I picked, but now the action that I pick is random, so it's d star of theta hat. So it's the difference between what I pick and the expected implementation probability.
Sorry, did you call that regret?
I call these the expected regret.
Expected regret.
Yeah, it's called expected regret because the loss is the regret loss. But it's still risk. It's just yeah, this particular form. Yeah, no problem. So let me just work this one out explicitly. So that's this is the expected value of the decision rule. So this is the same as the probability under theta that theta hat is larger than 0, because that's how frequently I implement the rule. And this is the same as the probability that theta hat minus theta is larger than minus theta. I'm going to divide everything over sigma, just standardizing. This is the same as the probability that a normal 0, 1 is larger than minus theta over sigma. And I can flip signs of the inequality and just say this is the probability that another normal, not necessarily this, but just the sign flip version of this one, it's the same as this one. Right? And so this is just a normal CDF at this point. Right, so one thing that you can see over here is that this regret function is going to be symmetric around theta. So if I really want to get the worst case over theta, it is enough for me to look at what happens for positive values. So I don't have to worry about this one. So the supremum over R, the supremum over theta in theta of RT star of theta is going to be the same as if I just maximize over large values. Everything is symmetric, so there's going to be a maximum. Whatever I found on the right, I'm going to also find it to the left of 0. So this is theta pleasure. And this is just an optimization problem that has a, I mean, you can show that this problem has a unique solution. So there's a unique value of theta over which this is optimized. And so that means that if you look at what the regret function is for this star as a function of theta, it's going to look something like let me call this theta star. Okay, so this is going to be the upper bound for the regret. It just looks like this. But now I'm going to try to give this rule a chance to also show up in the lower bound. And the way I'm going to do that is by trying to recover this rule as a base rule. So I'm going to consider a prior that is supported exactly on this point, and I'm going to give probability half-half to each of them, right? By the thing that I just erased, the base rule for that prior is just a rule that implements if the threshold is above 0, right? So that means that the average risk, so let me do it over here. Excellent. So consider the prior pi. So it's kind of like the same thing that we were doing before, supported on. Just going to repeat the graph so that it's clear what theta star and minus theta star are. Right, and I'm going to assume that pi of theta star equals 1/2. Right, so we've shown that the base rule for this prior is D star. And so now I'm going to try to use the bound in A, right? So the bound in A just tells me that a lower bound for minimax regret is the average risk, right? But under this prior, the average risk only takes two values, right? So it's the risk at theta star with probability 1/2 and the risk at minus theta star. So this would be but this is the threshold rule, right? So the risk of the threshold rule, just because how we work this thing in here, is going to be theta star times 1 minus phi theta star over sigma, right? That's the risk. So this part over here is going to be theta star 1 minus phi theta star over sigma. And I told you that this function is symmetric, so if you put it at minus theta, you're going to get exactly the same thing. So because of the symmetry, the overall average risk is going to be given by this, right? So this provides a lower bound, but so if you replace this expression, the sup, by the value that optimizes this, you've matched the lower and upper bounds. So this rule is minimax regret optimum. So one other thing just to conclude this thing is that, there is a sense in which the prior that we used to do this lower bound was a prior that allowed us to or helped us to match the lower and upper bound, right? So in a sense, these lower bounds became larger as I picked pi in a smart way, right? So I'll give you a quick definition next class, but in this particular case, the pi that we found is typically called the least favorable prior. So least favorable prior because it's intuitively it's the prior that is pushing this lower bound to be the highest, but it's also kind of like the prior that makes the minimax regret rule to be base. And again, here in this problem, we have that it's a threshold rule, right? So it becomes, it's admissible because of the arguments that we give. So now you have a rule where you don't need to pick a prior. It's based for a particular prior, for the least favorable prior. It's minimax regret optimal, and it's trivial to implement, right? It's Jake.
Just to tie this back to what Omar asked in the beginning of the class, I think, or maybe you can follow up if I get this wrong, but I think the kind of naive idea is to say something like minimax corresponds to some priors, so let's pick like some worst case prior, and that's essentially what we've done here. But we've done it in a smart way where it's not just the worst theta, it's some combination here, right?
Absolutely, absolutely. And just one thing, I mean, this is one particular approach of solving these minimax regret or minimax problems, which is kind of like I was clever enough to solve for the to find this least favorable distribution. I cannot do that all the time. I mean, this least favorable distribution need not exist. Sometimes things are more complicated, but there's still other ideas that are pretty helpful to think about lower bounds. So, and I'm just going to mention it, and this is the last thing. The lower bound that I gave you in here, right? It was replacing just the worst case risk by the average risk. But another way that you can use to try to figure out lower bounds is by restricting the set of points in the parameter space where you're looking at. For instance, say if you take, instead of the whole parameter space, you take only 2 points that are symmetric around 0, that would give you a lower bound to this problem, right? And then you can try to figure out, well, if I have those 2 points, and I'm trying to look for the supremum, right? I can try to further think about what type of decision rules would be, will give me the smallest value of this worst case risk for this 2-point problem. So it's more manageable because now I don't have to search over the whole parameter space. You're just looking at the payoff that you get at these 2 points. So these, there are a bunch of techniques out there because we have this statistical decision theory, but these minimax problems, they appear all the time when you're looking at non-parametric statistics. And so some of the techniques that they have for thinking about how to do bounds, in some cases it's not possible to give an exact thing. But there's a lot of work just showing that the rates at which the lower bound and the upper bound converge are the same, and that's kind of like the idea behind the minimax rates. But so this idea of discretizing the parameter space, it's usually called, I think, Lecam's method, and there are a bunch of other approaches to do it. There's a Fanos method, a Swartz method. So if you just Google those things, that part I never teach it in my class because it's get a little bit more complicated, and I haven't really used them in my work. But there are other things. I mean, they're not recipes, but they are approaches that you can follow. But I wish Jose were here because he's really good solving these minimax problems in all different versions. We have a paper together with just. Figure out a way to solve a minimax problem that I didn't even really see coming, and but it'd be good to check with him, like if he agrees with these things, that it's a lot of manual work on these things. Now there is a little bit more of work on thinking about algorithms to just try to solve these problems, but you know, the literature is more recent. Gary Chamberlain has an old paper in proposing an algorithm for solving these minimax problems when you have a discrete state space that builds on some of these ideas of algorithms for solving the equilibrium of two-person zero-sum games. So yeah, so I think that's it for today. Cool, awesome.